Hello everyone, and welcome to the second lecture of the course Introduction to Media Engineering. Last time we talked about the introduction and we explained the different types of media and what digital multimedia is and how the evolution of digital multimedia occurred over the years. We ended with talking about the outline. So the first topic in the outline of the course is digital representation of media, which we will cover in this lecture, which is mainly how we are going to represent those the different types of media that we talked about in digital form. Okay, so this is what we will cover in this lecture. So in order to represent data in digital form, we have to, of course, store it in a computer. So we'll start with the definition of how digital data looks like. So first of all, a bit represents the smallest digital quantity, which you already know. Bits are units of data that can only have one of two values, binary, which is either 0 or 1. A byte consists of 8 bits, where this is called the least significant bit, and this is the most significant bit. A word could be multiple bytes, like this is 2 bytes, a word that consists of 16 bits, 1 byte, and then another byte. Now, when we talk about the memory sizes throughout the course, so of course a kilobyte is equal to 1024 bytes, which comes from the fact that you would have 2 power 10 bytes, so that's why it's 1024. 2 power 10 is equal to 1024, or 1024 bytes. And then a megabyte is 1024 kilobytes. Now, there is a difference between talking about memory sizes and when we talk about bit rates in communication, which is how bits are transmitted. So when we say that we have kilobits, when we refer to the transmission of data over some communication channel, kilobits would be, or 1 kilobit is equal to 1000 bits, okay? So this is just something that we will use throughout the course. When we talk about kilobytes, when we talk about memory sizes, a kilo here is like 1024. While when we talk about bits for transmission, a kilo here is 1000 bits, okay? Now, 1 byte of data can represent multiple things. It can, or it could represent a character, like text, when you write in text, like character A, B, C, or so on, a pixel in an image, or a pixel in a video, okay? By a pixel here, we mean if you divide the image into rows and columns, so every single point or single element in that matrix, we would refer to it as a pixel. So the thing is, a byte of data can represent any of these things. What decides what a byte represents is how it is actually interpreted by the computer. So as an example, if you have the value of 106, okay? So 106, if you convert it into binary, you will have a certain arrangement of bits. Now, 106 could represent the small letter J if the value is interpreted using the Ascii code. You probably know what the Ascii code is. This is a code that has been made in order to define some binary pattern for every character you have in the keyboard, okay? So the value 106 in the Ascii code represents the letter J. However, if 106 is representing a pixel in an image, a grayscale image, which means that this image doesn't have color, it only has gray levels from black to white. So 106, and one more thing, and we will talk about this later on in more detail, but when we talk about grayscale images, the number 0 always represents black color, and in that case, every pixel, every point in the image, so if this is, let's imagine this is an image that has 4 columns and 3 rows, just a simple example, okay? If this image is a grayscale image, which means it doesn't have colors, it only has gray levels, then every pixel is in fact represented with 1 byte, okay? Now that 1 byte, which consists of 8 bits, the value that you have in that byte would represent the gray level of that pixel. So if the 1 byte is, let me write it here, If it's all zeros, like 1, 2, 3, 4, 5, 6, 7, 8, okay, all zeros, which means if you convert all zeros, of course, to decimal, you get 0. This is the representation of black. However, if it's all ones, you have 8 ones next to each other, so 4, 5, 6, 7, 8. If you convert 8 ones in binary to decimal, you will get the value, which is 255. This is in decimal. So that number, when you have that byte has all its bits equal to 1, this means that that pixel is white. If it's all zeros, it's black. How about if it's just a combination of ones and zeros? Like, for example, what if that one byte is equal to 101101111, for example? What would that represent in that case? It would represent some shade of gray between the darkest value, which is black, and the brightest, which is white. Okay? So the value 106, this value here, if we convert it from decimal to binary, and we see on the scale from black to white what this number represents, it will actually represent this shade of gray. So 106 would represent the small letter J if you are representing, if that byte represents an ASCII code, and it would represent this shade of gray if the value is interpreted as a pixel in an image. Okay, so that's why we're saying that, okay, whatever the type of data that you are storing, or it will be represented in binary. Now, how the computer will interpret that, this will determine what this value will map to. Here it maps to an ASCII code, while if it's an image, this grayscale image, it will map to this gray level. Okay, so let me erase this. The other thing about bits, other than that they represent data, bits also represent instructions of a computer program and memory locations. So I'm not sure if you had a course before on computer organization or architecture, but you probably know that in any computer system, there would be what's called a set of instructions. For example, one instruction is like one operation. This computer can do addition of 2 bytes, it can do subtraction, it can do multiplication. Now, the instructions that this computer is supposed to do, okay, will also be represented in binary as bits as well. In addition, memory locations. If you have a certain memory, like let's say you have RAM that has 4 gigabytes, for example, every memory location in that RAM will have an address, and that address will be represented with bits. So overall here, regardless if you are representing data or representing instructions or memory locations, all of them would be represented using binary bits in that case. Okay. So now, given that data will be represented in a computer in digital form, then we have to talk about the process of digitization, which is if you have data that's not represented in bits, it's not in digital format, how can you convert that data to be in digital format? So the data that's not in digital format is called an analog data, and analog data must be converted to digital form before it can be manipulated by a computer program. So what's the difference between analog and digital? Analog means that you have a continuous time signal, while digital means that you have a sequence of discrete values. This is like a very simple representation of time. This is time in digital form, while this is time in analog form. Okay. So the main difference between analog and digital is that in an analog signal, at any time point, if you would like to go and find the value of that signal, you will have a value. No matter what time point you choose, at any time point you go and check the value of that signal, you will find that there is some value. That value could be anything, could be 0, could be 1, could be 100, whatever, but there is a value that you will find at any time point. While in digital form, no, there is a sequence of discrete values, meaning that the data is not available at all time points. There might be some time points that you actually do not have data in them. Okay, so this is the main difference between analog and digital, and we will have more about this later on. But analog, as I said, it's a continuous time signal, It's like when you draw something, it looks like this. Let's assume an example. This is time, okay? And here, let's assume that we have a signal that represents the, let's assume it's like the voice amplitude of someone, okay? So you might have a signal that looks like this. So whatever I draw here, at any time point, like if you choose this time point, any time point, at any time point you can go and find the value for that signal. Now, when we talk about digital form, or mainly when we talk about discrete cases, this means the signal will be defined, for example, at this time point only, at this time point, at this time. So now if you try to go and find the value of that signal during this interval, okay, during this period here, there is no data. We don't have the data, okay? So this is the main difference between analog and digital. Now, why would computers try to deal with digital data rather than dealing with analog data? So maybe, I don't know if you asked yourself this question before, but when computers were designed, they were designed to deal with that type of data, which is digital, just binary, like ones and zeros, rather than dealing with continuous values, okay? And the main reason for this is that the circuits, electrical circuits that deal with those continuous signals, any small noise that might happen in the signal will change the value of that signal. For example, let's assume you have a circuit, and you probably had electrical circuits before, right? So let me erase this, okay? So if you have some circuit, like this is a battery, and you have a resistor here, another resistor here, like a very simple circuit like this one, and this is your ground, okay? Now let's assume that this is where we are measuring the output. So the voltage, we call it here VO, the voltage across that resistor, this is what we are going to measure from that circuit, okay? All right, now this circuit, if for any reason, let's assume this resistor here, for any reason, if that resistor actually changes with a little bit, like let's assume its resistance was 5 kilo ohms. Now what will happen if that 5 kilo ohms becomes 4.9 or 5.1 for whatever reason, okay? What will happen is the voltage that you will measure across this resistor will also change, okay? So if the change that happened in this resistor is because of some noise that's happening around that circuit, then the voltage reading that you will get out of the circuit will have this amount of noise contributing to its value, okay? However, if we deal with digital circuits, the thing about digital circuits is that when we talk about, for example, the gates, like AND gate, OR gate, you probably also have seen these gates before. Those gates, they output either 0 or 1, right? And when you measure the voltage out of that gate, so usually the range of the logic 1, let's assume we have an AND gate here, takes 2 inputs, outputs 1 output, okay? So that gate, logically, either it produces 1 or produces 0. Now, if you take the data sheet of the AND gate, the IC that has the AND gate, and look at what is the voltage that corresponds to 1, you will find that you have a range. It's not 5 volt exactly. Like, for example, if you have a voltage between, and you have to check the datasheet for that, but it's something like this, between 4.5, for example, and 5 volt, all of that is considered to be logic 1. While the 0, you will have, for example, voltage from 0 maybe up to 1 volt, for example. It could be different, by the way, depending on the IC. But from 0 to 1 volt is considered to be logic 0. And from 4 to 5 volt is considered to be logic 1. So what does this mean? This means that if you have some noise that happens within this circuit, such that the voltage is somewhere between 4 up to 5, all of that is considered as logic 1. While if it's between 0 and 1 volt, all of that is considered to be logic 0. So tiny changes that happen because of noise will still not affect the output of that gate. That gate will still be considered as the output should be logic 1 if you are between 4 and 5. Okay? Which means that you can rely more on those digital circuits or the concept of using those logic gates and the representation of binary data. It would be more reliable when we talk about having some noisy environments that could happen for whatever reason. Okay, so that's the philosophy behind having computer programs rely on digital circuits and digital data rather than dealing with analog data. Okay. All right. So, anyways, if you have an analog signal, like the example I had, a voice signal, and you captured that signal using a microphone, and then you would like to store that on the computer. You have to convert that analog signal because the voice, whatever that you're saying using a microphone, it's like a continuous time signal. It's something that has at any time point you'll have a value. Now we would like to convert that into a digital form, so we have to go through the digitization process. So the digitization process, let me erase this, consists of two operations. Okay, the first one is called sampling and the second one is called quantization. So to convert something from analog to digital, you have to do sampling and then you have to do quantization. And this is what we will explain next. Okay. So the first stage we called it sampling. And what is sampling? Sampling is measuring the analog signal at discrete intervals, and it would be defined with a parameter called the sampling rate, which is the number of samples that you take from that signal in a unit time. How about the second stage, which is quantization? I'm going to have an example next to explain what this is, but let's see the definitions. The quantization is to restrict the measured values. Those values that you measure in the sampling stage, they would be restricted to discrete levels. The parameter that defines the quantization is something called quantization levels, which are levels to which a signal is quantized. So let's have an example. Let's assume we have this analog signal. So what would be the output of the two stages, sampling followed by quantization? If we look at sampling as defined, measuring the analog signal at discrete intervals. You see here, the dotted curve that you see here is actually the analog signal. And then we measured the analog signal at discrete intervals, which is at this exact sample, and then at this sample, at this time sample, at this time sample. So in between we are skipping. We're not measuring the value of that signal. Okay, so we're measuring the value of the signal at certain time points. Okay, now this is sampling. Now the parameter that's called the sampling rate is the number of samples that you take in a unit time. So for example, let's assume that from this point, let me draw it here. Let's assume from this point to this point, this is, for example, 1 second. Okay, if this is 1 second, let's count how many samples we took in that 1 second. We have 1, 2, 3, 4, 5, 6, 7. Okay, so 7 samples per second, which means that the sampling rate is 7 hertz. So the unit hertz is the number of samples that you take per second. So if you take 7 samples per second, this means that you have a sampling rate that is equal to 7 hertz. Okay. Of course, as you increase the sampling rate, what will happen? You will have more samples from that signal, and therefore you will have a better representation of that signal. So let me talk about what do we need out of the sampling quantization. If you have an analog signal like this one and you would like to represent it in digital form, you would like to have the closest representation to the analog signal, but now in digital format. Okay, which means, for example, if you look at this signal here, there is up and then down and then goes up again. Okay, so now if you take those samples according to this sampling rate, which is, if we assume this again, this is 1 second, then you have 7 samples per second, which is 7 hertz. If you look at those samples, so it's as if you're measuring the value of the signal at this point, and then at this point, at this one, and so on. So it looks like this kind of sampling is capturing all the ups and downs of that signal. Now imagine that someone else decided to do sampling for the signal. I'm gonna draw it on the analog signal here. For example, taking one sample, let's talk about an extreme case. Measuring this sample, okay, and measuring this one, and then measuring this one. If you compare those samples, of course, they're not a good representation of that signal, because this way you are actually, if you're using only those 3 samples to represent the signal, this peak here is completely missed. You did not actually represent it. You're measuring the value of the signal at this time point and at this time point. How about this peak here? We have an up and then down. This is completely missed. This peak here also completely missed. Okay, so which means that as you increase the number of samples per second, or the sampling rate, you will get a better representation of that signal. Okay, so this is sampling. Now, what is the advantage and disadvantage of a high sampling rate? Of course, as you increase sampling rate, as I just mentioned, you will get a very good representation of the signal. So this is the advantage of having a high sampling rate. How about the disadvantage? What are you losing by having a high sampling rate? If you think about it, this means that you are storing more values from that analog signal, which means that if you're going to take those samples, the values that you measured, and then store them in the memory or on the hard drive, they will take, if you have 7 samples per second, then means that you have 7 values. Let's assume every sample will be represented with 1 byte, for example. Then 1 second of the signal will be represented with 7 bytes. Compared to if you use, instead of 7 hertz, what if you use 2 hertz? Then you're representing the same 1 second, but only using 2 bytes. So you will be, if you have a high sampling rate, you are actually increasing, or you will need more storage to store your signal compared to having a low sampling rate. So the advantage is getting better representation of the signal, but what you are paying, the cost here, is that you are using more space to do that. Now, this is the first step of digitization. Now, what is the second step? Second step is called quantization. So what is quantization? Sampling is just measuring the value of that signal at certain time points. So what is quantization? Again, it's restricting the measured values to discrete levels. So what do we mean by restricting the measured values to discrete levels? This means that the values that you get here, you will not store them as is. If you look at what is shown here in this figure, we defined here on the y-axis certain values only. So any sample that you are measuring has to be stored as one of those. Here we have 1, 2, 3, 4, 5, 6, 7, and maybe the x-axis itself is 8. So we have 8 levels that the samples that are recorded, they have to be approximated or stored as one of those 8 levels. If you look closely at this sample here, the first sample here, okay? So this sample, in the sampling step, you see the bar goes up to the signal itself. Now when we look at what happened here, the bar stopped at this level. So why? Because we only have, in this range, we only have, either we will have to store this sample at this level or at this level. We don't have in between, which is the actual value of that signal. So we are storing this sample to the closest level to its value, which is this value here. Okay, so we are restricting the values that we are storing. So the sampling defines what time points you will measure the value of that signal, while quantization defines the actual value that will be stored for every sample. So we are restricting in this example to only 8 levels here. So what is quantization levels? The number of levels to which a signal is quantized. In that case, it was 8 actually. Okay, so what's the advantage and disadvantage also of having large number of quantization levels versus low number of quantization levels? If you have a large number of quantization levels, you might be able to get better representation of the signal. So again, this sample here, the actual value of that sample in the analog signal was here at this point here. Now what you're actually storing is not that value, it's something lower than that value. So imagine that instead of having 8 quantization levels, what if we had 16 quantization levels? Most probably you would have had a quantization level in between these two. So therefore this would be better representation of that sample, because the value here is, as you see here, is in between these two predefined levels. So as you increase the number of quantization levels, you'll get better representation of the signal. However, what are you losing by doing this? Again, you're losing storage. Why? Because if you have 8 quantization levels, how many bits do you need to represent the 8 quantization levels? You probably know this already. In order to represent 8 different values, you need 3 bits. Okay? So, for example, the lowest level here would be represented with 0, 0, 0. Second one, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on until 1, 1, 1, which is the highest level. Now, if you increase the number of levels from 8 to 16, this means you need 1 more bit. So you need 4 bits instead of 3 bits. So as you increase the number of quantization levels, you need more bits to represent each sample, and therefore you will need more storage. So you will be wasting space in that case, maybe. So therefore, in general, we have 2 steps when we convert an analog signal to a digital form. First of all, we do sampling. We pick samples on the x-axis. As if you are on the x-axis, you're setting certain values that you're going to measure the value of the signal at. The sampling has a parameter called sampling rate, which defines the number of samples per second. Like here, as we said, 7 samples per second is like 7 hertz. Now, after you do that, you do the quantization. Those values that you measured, you approximate them to the nearest quantization level from the predefined quantization levels that you have. Okay? Now, the values that are the values of the quantization levels represent the values that will be stored for each one of those samples. Okay? So this is the process. Whether you are converting an analog voice signal, an image that is captured using a camera, a video, whatever, this is the general process of converting something from analog to digital, and these are the 2 needed steps in order to do that process. Okay. So as I said, the advantage of using digital signals that they are more robust than analog ones, as they do not suffer degradations when copied or transmitted over noisy media. Now, the next thing after you do digitization, so let's assume you had a signal, you digitized it, and then you stored it on the computer. Now, once you do the storage, if you would like to display that data one more time, you have to convert it back. You might need actually to convert it back to analog one more time. So, for example, if you have a voice recorded on the computer, okay, and then that voice has to be, if someone would like to hear it, like a piece of music or voice or something, if someone wants to listen to that, they have to be played through speakers. And the speakers, they are analog devices, they are not digital, so they deal with continuous time signal. But therefore, we need to, after we do the storage, if we would like to play back what we stored, we will need to convert back from digital to analog. So to reconstruct the original signal from the digitized signal, we need to decide how to fill the gaps between the samples, because the main thing that we lost when we converted from analog to digital, we lost 2 things. The first loss was in the sampling process, where in between samples we don't have readings. The second loss is that when we did the quantization, we approximated the values that will be stored to the nearest values. So the first thing that we need to do is, if we would like to convert that to continuous time signal, then the minimum you need to do is to fill the gaps between the samples. So one possible way to do this is to use what's called the sample and hold technique, or sample and hold reconstruction, which is, if we have those samples, okay, those samples were taken before they were stored, and they were taken and then they were quantized and they are stored on the computer. Okay, the dotted curve that you see here, this is the actual signal, the actual analog signal before doing the sampling and quantization, before digitization. Now, let's assume we stored those samples, and then those samples represented a music piece that will have to be played back through speakers. Then what we need to do is to fill the gaps between the samples. Otherwise, if we don't do that, we might hear that there are some like pauses in the music, like because in between the samples there is nothing. So if you only listen to this sample and then after some time you listen to the sample, so in between the two samples the speaker will not produce any sound, and therefore you will hear as if the sound is like jittery or it's actually broken. So what we need to do is to do this filling between the samples. The simplest approach is to use what's called sample and hold reconstruction, which is, this is our first stored sample. So to fill the gap between this sample and the next one, we just keep the value that we have here constant. So we keep it constant, and then we go to the next sample, which is this one. Now between this sample and the next one, we keep this value constant. So you get this one, and this one, and so on. So this would be the sample and hold reconstruction of this digital signal. When you compare this to the actual analog one, they look like they have the same somehow pattern, because we had a peak here, we have a peak here. There is a small peak here, we have a small peak here, and so on. Looks like we have the general shape of the actual analog signal, but of course we're not able, using this one, you're not able to exactly reconstruct the actual analog signal. Okay? One other approach other than sample and hold reconstruction is, from this one to this one, instead of going constant, we connect a straight line. So let me draw this here. If you are reconstructing that signal, so from this sample to this sample, we will have a straight line. Okay, let me erase this. Okay, so we will have like a straight line going from this to this, supposed to be a straight line, and then from this one to this one, another straight line, from this one to this one, another straight line, and here it's a constant, another straight line, and so on. So if you assume that I draw straight lines, I'm drawing with my hand, so it's not that really, with the mouse cursor, it's not that accurate, but these are supposed to be straight lines. But the thing is, you might see that this linear reconstruction, instead of doing the sample and hold, might be actually better in that case. Some other people, they even try to connect these with like second order polynomials, for example. Okay, so anyways, this is using sample and hold reconstruction, or even connecting the points with a straight line. Okay, so again, so once you do the digitization, if you would like to play back the digital data using an analog device, you will have to reconstruct or try to reconstruct the analog signal by trying to fill the gaps in between the samples. Okay, so this is the reconstruction phase. So comparing, as we said, the reconstructed signal to the original signal, some information is already lost, which is something that we cannot recover, but this is the best we can do. Of course, if you would like not to get a lot of discrepancy or difference between the reconstructed signal and the actual one, what you need to do is increase the number of samples and increase the number of quantization levels. However, once you do that, once you increase the number of samples and you increase the number of quantization levels, you will be actually using more storage to represent the same content. So there is no free lunch, of course. Okay, all right. Okay, so this actually takes us to a very important concept, in the whole course, this concept, which is the sampling theorem. What is the sampling theorem? The sampling theorem tries to find out what is the best way that we should sample a signal with, such that when we reconstruct it, we don't lose much. Okay, so to reconstruct the original signal from the digitized signal, we need to sample, and this is what the sampling theorem determines, at a rate that is high enough to capture the signal changes. So what do you mean by this? Let's assume that we have this blue signal. You see that blue sine wave? If we sample the blue sine wave at the red dots, okay? So imagine that you have this sine wave as a continuous signal, an analog one, and we are sampling it at only the red dots. You see those red dots? These are the samples that we are taking or measuring from that signal. What will happen in that case? If you, let's assume you take that red dot, these red dots, you store them, and then you try to reconstruct from the red dots the original signal. And let's assume that when we are doing this, we are going to use, you remember I mentioned in the previous slide, the connecting two dots with a straight line. If we do that, let's see what will happen. So from here to here with a straight line, from here to here, a straight line. Straight line, you see, I'm trying to connect the dots with a straight line, even if we go with not straight line. So what do you see now? So we had those red dots, the samples that were stored, okay? And then we are reconstructing from those samples the analog signal. We get this signal. Now, what is the relationship? What's the similarity between this red signal and the blue one? There is actually no similarity. In fact, this is a sine wave that has a very, very low frequency compared to this sine wave. You know the frequency of the sine wave, as the frequency increases, you get more peaks, ups and downs, or peaks and valleys in the signal than when you have a low frequency. A low frequency is something that varies very slowly. So what happened here, when we sampled the blue signal at these red dots, these samples specifically, and then did the reconstruction, we got a sine wave that's completely different from the original signal. So this is not a good representation. If the target after doing the digitization is to play back, you store things in digital format and then you try to play them back through an analog device, okay? If this is the objective, then what you will play back in this case is a completely different signal from the original one that was stored. So sampling the blue sine wave at the red dots produces a sine wave with a frequency that is much less than the original sine wave. So what's the solution to this? The sampling theorem, as we will see in the next slide, tries to find the solution to this. It tries to answer this question, which is, what is the optimal sampling rate, or the number of samples per second that we have to use in order for the reconstructed signal to be as close as possible to the actual analog signal that was digitized in the first place. Let's see another example. So the same effect actually might happen in images, something called Moire Pattern. You look at this image here, okay? Now, if we shrink that image, this is what we get. So what do you notice here? If you look at this closely, what do we notice here? First of all, looking at this original image, what do we have? We have this wall, you see this wall here? It has bricks, like if we, let me clarify this. If we zoom in on any section, okay, and look at what it has like these lines, okay, and there are those stones or bricks that make the wall, okay. This is what this any part in the original image would look like. Now, what will happen if we shrink the image? How do we shrink the image? Simply, the simplest way to do shrinking of an image is to drop rows and columns from the image. For example, if you'd like to decrease the number of rows by half and the number of columns by half, what you can do is take the first row and then drop the second row. Then take the third row, store the third row, and then drop the fourth one, and so on. And do the same with the columns. What you will end up having an image that has half the number of rows and half the number of columns of the original image. Now, what do you notice when you look at this here? What we notice here is that we have these lines. You see these lines here? And these lines, you see like these lines are getting repeated somehow, and they were not actually, they do not exist in the original image. What existed actually in the original image is the lines of the bricks, the lines between the bricks here. But now when we did the shrinking, we got new lines that are not actually present in the original image. This is very similar to what happened here. When we did the digitization, what happened? We got a completely new different signal that was not present in the original one. So imagine that this original image is the actual scene, and you're taking a picture of that actual scene with a camera, and the image would be that size. Okay, you see now you have lines appearing in the captured image that are not present in the original one. This is what's called Moire pattern. Moire is the name of the guy who actually found out this property. And in fact, what we have here is a new frequency that's appearing in the image. So what is the concept of frequency? And we will talk about this more later on. The concept of frequency is that there is something that gets repeated. Like this sine wave has a frequency. Why? Because what's the frequency of a sine wave? It's 1 over the time between, for example, the 1 over the period. And the period can be measured as the time between two successive peaks, for example. Okay? So 1 over the period, you get the frequency. Okay? Now, the frequency in that case represents something that gets repeated. If you look at this image here, we have in this image lines, and those lines, they get repeated, like lines, bricks that get repeated over and over. You see this line, this line, this line, these lines are getting repeated. Okay, so we have some sort of frequency, something that gets repeated in this image. Now, when we did the shrinking, or when we captured this original scene into an image that has a small size, we got new lines that get repeated also, but with a new frequency. And the frequency, the repetition rate of those lines is different from the repetition rate of the actual lines that were in the original image. Okay? So all in all, what we want to say here is that if you have an analog signal and you sample it, but your sampling rate is not high enough, it's small, like what happened here, if you have more samples in between the red dots, you might not have this bad reconstructed signal. You might be able to capture more of the original one. But if your sampling rate is not high enough, what happens is that you will get a signal that is completely different when you do the reconstruction, completely different from the actual signal. It's not close at all to it. The same in images. So the sampling theorem is trying to fix this, tries to tell us what would be the sampling rate, how many samples per second do we need for this signal, so that when we store it in digital form and then reconstruct it, we get something that is close to the original one, not as different as it happened here. Okay? So given that this sampling theorem is related to the frequency domain representation, and we talked about the concept of frequency, so we have talked about what the Fourier transform is. The Fourier transform, probably you had this in other courses before, the Fourier series and Fourier transform concept. The Fourier transform operation can be used to compute a signal's representation in the frequency domain. So, for example, if you have this signal here, this is like a sine wave that has a period of 0.2 seconds. Now, which means if you convert it to frequency, that you have a frequency of 1 over 0.2, which is actually 5 Hertz. Now, when you represent this signal in the frequency domain, this is what you will get. On the x-axis, instead of having here time, so this is something that varies with time, now you have frequency. On the y-axis, you have the amplitude of that frequency. So for example, since this signal has a frequency of 5 Hertz, then what we will have here is at exactly 5 Hertz, which is the frequency of that signal, we'll have a very strong peak. While at all other frequencies, we have nothing. So this is an indication that the signal if this is the frequency domain representation of a signal, that signal in the time domain has a frequency of 5 Hertz or a period of 0.2. Okay, so this is the main idea of doing the frequency domain representation. Now, what if instead of a sine wave like this one, we have a sine wave that has a period of 0.2, in addition to it another sine wave that has a frequency or a period of let's say 0.1. Okay, so let me write this down. So if you have a period of 0.2, meaning that you have a frequency of 5 Hertz, then this would be sine, it's when you do the sine wave, it's sine of 2 pi ft. Now if f is equal to 5 Hertz like in this example, then 2 pi ft would be equal to 10 pi multiplied by t. So that signal, sine of 10 pi t, the time domain is what we have here. This is the time domain of the signal, and this is the frequency domain of the signal. Now what if in addition to sine of 10 pi t, we have plus sine of another sine wave that has, let's assume a frequency of, let's assume it's 1. Okay? or let's make it 10. Let's assume we have a frequency of 10. So 2 pi ft would be 2 pi multiplied by 10. So we have 20 pi t. Okay. How would the frequency domain of this signal, these two sine waves summed up together, how would the frequency domain look like? You will have a peak at 5 Hertz because of this sine wave, and then because now you have a signal that has a frequency equal to 10 Hertz, then at 10 you will have another peak. Okay. Of course, what I'm saying might not be entirely accurate because there is something called the harmonics of the signal that also appear, but for now let's just keep the main idea is that if you have multiple sinusoids added together that have different frequencies, those frequencies will appear in the frequency domain representation, will have strong amplitude compared to other frequencies. Okay. So this is the idea of having a time domain signal, like the signal that we have in this example here could actually represent the audio or some voice, for example, of someone. This is its frequency domain representation. Okay. Now, how about the concept of the frequency when we talk about images? So in the previous example we had in the previous slide, we said we have a signal that varies with time, right? Okay. So you remember in the example when we talked about the Moire patterns, I mentioned that there is some repetition that happens in the image that converts to frequency. So the concept of having a frequency is not only specific to time domain signals, it can be also applied to things that vary with space. So what do you mean by a spatial signal? So when you think about an image, the image has some gray levels that vary with the position in that image, meaning that in the space, not in time. Space here means, so when we say spatial domain, we mean by this locations and not time samples. Okay? So, for example, if you look at this, let's assume that this is a single row of an image. So let me draw it here. We have one row of an image. Okay? Remember when I mentioned the values of the grayscale in the beginning of this lecture, we said that black is represented with 0 and white is represented with 255, and the gray levels would be values in between. So imagine that you have an image that has just a single row of pixels, not multiple rows. And the value that we have here, this is 0, then this one is 128, the next one is 255, and then 128, and then 0, and then 255, and then 128. So it looks like the gray levels here are oscillating, like 0, 128, 255, 128, 0, and so on. Which means if I plot it, let's imagine that we are representing this in a different way. 0 would be the value here, 128 would be the value here, 255 is here, and then 128, and then 0. Actually, this, let me correct this one. This is supposed to be 128 to follow the same cycle. So here we have 128 and then 255. So this would be 128 and then 255. So if you connect the dots, it's like you have somehow something like a sine wave that is oscillating. But now this sine wave is not oscillating over time, it's oscillating over space. Okay? Now, if the distance between two pixels is equal to 0.2 meters, let's assume this assumption that the distance physically between two pixels is about 0.2 meters, like 20 centimeters. For example, let's assume this is the case. Or sorry, I'm sorry about that. But let's assume that the repetition from here to here, okay, so when the signal gets repeated, it gets repeated with a period of 0.2 meters. Now, if you take those values and compute the frequency domain representation of them, you will get the same thing, 0.2 meter, this is your period. So the frequency is 1 over the period, 1 over 0.2, which is 5 Hertz as well. But here, the Hertz is different. The representation relative to space, not relative to time. So the reason I'm mentioning this is that I want you to know that the idea of having frequency domain representation is not only restricted to time domain signals, things that vary with time. They are also applicable when we have something varies with space, like pixels in an image. In that case, they are varying with distance, space, like here the period is in meters, you're measuring it in meters. So regardless of if it's represented with respect to time, represented with respect to distance or space, it's the same thing. You have the concept of frequency holds as well. Okay. Now the idea of the frequency domain representation is that any signal, whether spatial or temporal means it varies with time, spatial it varies with space, as I explained, they are actually made up of pure sine wave components at different frequencies. So let's see this as an example. If you see this red curve or red plot, it's like a square wave that gets repeated over and over for until infinity. Okay. Now, if you try to approximate this red curve using a single sinusoid, this is if we approximate it with sine of x. So the blue here is just sine of x. So it looks like it has the same frequency of repetition, but of course the blue signal doesn't exactly match the red one. There is a difference between them. Now, what will happen if we add to sine of x sine 3x over 3? So now we have two sine waves added up together, and this is what you see here. And now you see like these two sine waves, when they are added together, they are getting close to the red curve. Okay, they are much better than just using a single sine wave. What if we add another one, sine 5x over 5? Now this sine wave, this signal, the blue one, has three sine waves added up together. So now it's getting even closer to how the red one looks like. What if we add sine 7x over 7, sine 9x over 9? What if we go up to sine 101x over 101? You see now the blue and red, they are almost identical. So this tells us that any periodic signal can be represented with a summation. This is the idea of Fourier series, the summation of multiple sine waves. Now, if you look at that in the frequency domain, then this is what you will have. You have a peak at f, a peak at 3f. So why f and 3f? F represents sine x, 3f represents the sine 3x. Now, because sine 3x is divided by 3, the amplitude at 3f is lower than at f. 5f, 7f, 9f, and so on. How about the negative ones? This is just nothing. You can ignore the negative part because this signal is always symmetric about the origin. Okay? At 0, you have a value, and that 0 value means this is the DC component, which is you are raising the sine wave to match the amplitude of the red curve. Okay? So anyways, any signal can be factorized into a summation of multiple sinusoids, like we did in this example for this periodic signal. Okay? Now, one important thing here to notice is that the high frequencies, they are associated with the abrupt changes or the sudden changes. You see here when we have a very low frequency, which is just sine x, we had a very slow signal. Okay? When we add the sine 3x over 3, now you see the blue curve is getting more, the transition from the low to high is happening at a higher slope or more suddenly compared to the slow one here. Now when you add sine 5x over 5, it gets more steep. Sine 7x, you see like when we went up to sine 101, we have this very sharp transition from low to high. So the high frequencies are always associated with the sudden changes that happen in the signal. Just remember this property because we will need it in some other cases. Okay? So finally we reach what the sampling theorem is, which is going to answer this question. You have an analog signal, you would like to digitize it, so you'd like to find what's the is there a way to choose the sampling frequency or the sampling rate such that when this signal is reconstructed we get something that is close to the actual analog signal. So the sampling theorem states that if the highest frequency component of a signal is at fH, the signal can be properly reconstructed if it has been sampled at a frequency greater than twice fh. And this is sometimes called Nyquist Threat, after the name the person called Nyquist, who actually proposed this theory. Probably you have seen this before at some point. So it says, again, if you have a signal and the highest frequency component, which means if you take that signal, apply frequency domain representation, whether for a series or Fourier transform, and you found out that the highest frequency in that signal is fh, then this signal can be properly reconstructed from its digital form if it has been sampled at a frequency greater than twice fh. So let's have an example just to explain this idea. So let's talk here about the undersampling, which leads to aliasing, or the concept of Moire pattern that we saw in the previous slides. Let's assume we have line that rotates clockwise at n rotations per second. So imagine that you have line in front of you, and that line is rotating clockwise, similar to how a clock works, but this line is rotating at n rotations per second. Okay, now from the let's assume that you're now capturing a video of that line while it rotates, and you decided to take samples from that video, and those samples are at a rate of 4n times per second. So the line rotates n rotations per second. Now we are sampling at 4 times this rotation speed. So first of all, if the line rotates at n rotations per second, let's assume that this number n is let's say twice per second. So every second it rotates 2 times. Okay, now what will happen if you are going to sample it at 8 samples per second? Okay, for n, if n is equal to 2, so you have 8 samples per second. So here we have 1, 2, 3, 4, 5, 6, 7, 8. So these are the 8 samples. Now let's see what happens here. Because you're sampling at 4 times the rotation speed, you have the first sample. Let's assume this is the first sample here. Second one will be here. The third one will be here. The fourth one will be here. Now the fifth one will, again, this will keep repeating because this one is rotating n rotations per second. So this, if this sample is here, it will get repeated here, and it will get repeated here. Okay, so let's assume that this is 4 times per second, which means if you look at this pattern, we are capable of detecting that this line is actually rotating clockwise. Why? Because the first sample we saw, we have the line here. Second sample, the line is here. Third sample, the line is here. Fourth sample is here. Fifth is here. So this means that the line is rotating clockwise. Okay, now what will happen if you sample this or you take samples for that video, but at a frequency of 2n? Okay, so exactly twice the rotation speed. If this is 4n, then 2n would be half that number, right? So you have instead of having let's assume for now that n was 1, just to simplify. Okay, so if n is 1, then you have 4 samples per second. So this is 1, 2, 3, 4. These are the 4 samples per second, and this is the second, and then the third second, and so on. What if you are sampling at 2n, meaning that you have only 2 samples per second? You will have this one, and then you will have this one. How about the one that we had here? It will be dropped because you're only keeping 2 samples per second. So you have this, and then this, and then for the second you have this one, and so on. So now when you look at this, let's assume you're only viewing this. You see this sample, the line is up here. Second sample, the line is down. Third sample, the line is up. Fourth sample, the line is down. Now if someone shows you this and asks you which direction is the line rotating, is it rotating clockwise or anti-clockwise? Now from this pattern you would not be able to tell, right? Because we need to see the intermediate positions of the line to be able to tell if it was rotating clockwise or anti-clockwise, like what we have here. So this is 2n, right? Now how about here? We are sampling at 4n over 3, like 1/3 the sampling rate that we have here, meaning that for every 4 you see, like every 3 samples we are keeping 1, every 3 we are keeping 1. Okay, you see this sample, and then we are dropping these 2, and then we are taking this one, and then we are dropping these 2, and then taking this one, dropping these 2. Okay, let's assume these are the samples. So when we say 4n over 3, it's like 1/3 the sampling rate that we had here. Meaning that if you count how many samples we have here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10 over 3. So 10 over 3 is 3.33 samples. Here, approximately, it's like up to 4 in that case. Now, regardless of this, let's look at the samples that we have here. Now, the first sample was here. The second sample that we will see, we will not see all of that. We will see this one where the line is in this direction. The third one, the line is down here. The fourth one, the line is here. So what does this indicate? If someone shows you those samples and asks you which direction is the line rotating, what will you see? You will see that it's as if the line is rotating actually clockwise. Anti-clockwise here. Although in reality it was rotating clockwise. Now when you view those red samples, you will get the impression that the line is actually rotating anti-clockwise, which is opposite to its actual direction. Now, going back to these numbers, here we were sampling at 2n. So what is n again? N is the number of rotations per second for the line. This is as if this is fh. This is the frequency that you have in the video. Something that gets repeated every a certain time with that frequency, n rotations per second. This value was twice 2n, which in fact, according to this theorem, it's equal to 2fh. It says here that if the highest frequency component signal is at fh, the signal can be properly reconstructed if it has been sampled at a frequency greater than 2fh. Here you are exactly at 2fh. So still you wouldn't be able to distinguish if the line is moving clockwise or anti-clockwise. Now this 4n over 3 is obviously less than 2n. Okay, it's actually 1.33n. So this is below the Nyquist rate. That's why here when you look at those samples and you try to imagine how the line is rotating, it's actually rotating in the opposite direction. So it's not a good reconstruction in that case. You're not representing the actual data in a good way in that case. Now, how about if you have 4n? What is 4n? How is 4n related to the Nyquist rate? It's double the Nyquist rate. So what do we have? We can actually see that the line is rotating clockwise. So out of this example, we get the concept of that if you have something in analog form like this, rotating at n rotations per second, if you sample it at higher than the Nyquist rate, you will be able to detect the actual data that were in that analog signal, which is that actually the line is rotating clockwise. However, if you sample at below the Nyquist rate, which is below 2n, you will get wrong information. You get what's called aliasing, or like these false patterns that did not exist, like this false information that you will get the impression from here that the line is rotating in the opposite direction, while in reality it was rotating actually clockwise. However, at the sampling rate exactly, it will be ambiguous. You wouldn't be able to tell if it's moving clockwise or anti-clockwise. Okay, so again, this is the main concept of the sampling theorem that tells you that if you would like to sample some analog signal and reconstruct it, so you're sampling it because you're storing it in digital format and you would like to go back to the analog. So in order to be able to get a good representation of the analog signal in digital form, you have to sample at least twice or greater than twice the highest frequency, the thing that gets repeated in that analog signal. Okay, let's see some examples in the next slide that will explain this idea even more, and you will get the general idea more in that case. So we will see here two examples, one from video data and one from audio data. So the first one is called the Wagon wheel effect. You probably have noticed this before. I'm going to show you the video and then you'll see what I'm talking about. Before we run the video, so this video was captured at a rate of 30 frames per second. So every second, okay, in time, we are storing 30 frames per that second. Okay, so let's see what we have here in that case. Let's see what will happen in this video. So what you see now is that it looks like the wheel is not turning. However, in reality, it was actually turning because the car is moving. So I probably have seen this in movies before. Why is this happening? This is happening because the 30 frames per second were not high enough to capture the rotations of the wheel, right? So you remember when we, in the previous slide, when we talked about that there is a line rotating at n rotations per second, right? And we had to sample at above the n, okay? Now, let's imagine here, so in this case, what if the, in this video, what if the tire was, or the wheel, the tire here, was rotating at, let's assume 50 times per second. If it rotates at 50 times per second, then to be able to see that this wheel is actually rotating in the right direction, it's actually rotating in, you need to sample at least twice this number, which is 100 frames per second. Given that we saw here that the wheel is static, it's not moving at all, then most probably, or this is actually what's happening, this frame rate is not high enough to capture the rotation of that wheel. Okay, so that effect that you see in many cases in movies and in other things is probably, they call it the wagon wheel effect. It's happening because the frame rate, the number of frames that are stored per second in the video, that number is not high, is not sufficient enough in order to capture the rotation of the wheel or the tire in that case. Okay, let's see another example from audio. Okay, in that example that we will see the effect of also undersampling or storing less number of samples in audio. Here, this audio that we are going to hear has a sampling rate of 11.025 kilohertz. Okay, so this is the sampling rate, which means that every second we have 11.025 multiplied by 1000 samples recorded. Okay, now what we will hear in the audio is that the analog signal that is being sampled at this rate, its frequency was being varied starting from 0 and going up to 20 kilohertz. Now, if I'm telling you that the sampling rate is 11.025 kilohertz, if someone tells you I have a sampling rate of 11.025 kilohertz, then according to the sampling theorem, what is the maximum frequency that should be present, or what would be the maximum frequency of the signal so that the 11.025 kilohertz would be sufficient? Remember what we mentioned before is that the Nyquist Threat says that in order to sample a signal that has a highest frequency of FH, you need to sample it at greater than 2 FH. So your sampling rate should be above 2 FH in order to be able to see that signal as you recorded it. Now, if I'm telling you that the sampling rate is 11.025 kilohertz, this means what is the maximum frequency that should be present in that signal such that you would be able to reconstruct it efficiently or in a good way without losing anything. It actually means that your FH should be this number divided by 2. So if your signal has frequencies up to half 11.025 kilohertz, you're fine. You will be able to hear that frequency. Now, if your signal has frequencies that are above the half of 11.025, then when you are reconstructing, you will not be able to hear those frequencies as they should be. Now, before we listen to the audio, I'm just trying to describe you what you will see in the audio. One more thing is that I don't know if you have heard before how a sine wave sounds. A sine wave would sound like a constant tone. Now, as the frequency increases, that tone it gets repeated much faster, and it will appear as if that sound is getting like thinner. Okay, let's hear the this audio. Okay. Here. So what will happen now, what you will see is that the actual, before we run it, the actual audio that we have, the audio signal, it has frequencies starting from 0 and it's increasing that frequency gradually, okay, up to 20 kilohertz. Okay, so let's see what will happen. So you're hearing now the sine wave. Notice here, so all that, the sound is getting thinner, thinner, higher, looks higher, until you reach this point, and then it goes back. So why is it going back? It actually started going back after reaching that point. That point, which is around 5.5 kilohertz. That point, the 5.5 kilohertz that we have here, is half this number, 11.025 kilohertz. So although the actual sound was increasing in reality, the one that we recorded is increasing in reality up to 20 kilohertz, okay? However, once we reach the 5.5 kilohertz mark, which is half the 11.025, it appeared as if the sound is having less frequency, because you saw the curve was going backwards, and even the audio that we were listening to, the sound is not getting that high frequency that we were hearing, where we started getting less frequency. So although in reality the frequency was increasing beyond the 5.5, it was going up to 6, 7, up to 20 kilohertz. However, what we were hearing appeared as if we have lower frequency. Why is this happening? Again, it's because the sampling rate is not high enough. It's only 11.025 kilohertz. So we got what's called aliasing. So in images, it happens as Moire patterns, as we saw. In videos, we get what's called the wagon wheel effect. Something would appear not as it is in reality. In audio, you get what's called aliasing in that case. Okay? All right, so that's it for this lecture. In this lecture, we covered how we digitize data, how we do sampling, how we do quantization, and we talked about the sampling theorem and the effect of increasing the sampling rate and decreasing it, and what happens when we do not respect the sampling theorem. Okay? All right, that's it, and I'll talk to you soon, inshallah. Goodbye.